Remember that fluid distribution is a function partly of the kidneys. About 2/3 of the body fluids are intracellular. What surprises me is that 25% of the body fluid is interstitial. Can you imagine? 25% is interstitial in the third space. I thought we weren't supposed to have anything in the third space, right? Well, it turns out we do, and it's quite a bit of fluid in that third space. So fluid balance has to be a balance between daily loss and daily intake. So daily intake is, 2 or 3 liters a day, and that gets divided between fluid intake, food intake, and then there's some water that's produced during metabolism, right? During the metabolic process. So for instance, this is just to tease you and get you ready for the rest of this today. In the liver makes BUN. Well, it makes BUN because it combines ammonia, which is a product of protein metabolism, plus CO2, and you get blood urea nitrogen plus, guess what? Water. Got to balance the equations, right? Stoichiometry, remember that from chemistry? Always got to balance your equation. Make sure you got the right stuff on both sides. So water is produced about 300 cc's from metabolic processes, such as creation of BUN. The electrolytes exist in different concentrations in different parts of the body, right? In different silos, so to speak. So remember that cations, which I always thought should be cations, but whatever. Cations are positively charged, anions are negatively charged, and they exist in 2 spaces. They exist either extracellularly or intracellularly. Well, we remember from talking about neural signal transmission and cardiac dysrhythmias, etc., that the majority of the cation that's extracellular is sodium, and the majority that's intracellular is potassium, right? Well, there's also anions that go along with those. So phosphate is an intracellular substance, and chloride tends to be in higher concentrations outside the cell. So the major anions plus the major cations form a homeostatic mechanism, right? When the cation charge equals the anion charge, that is homeostasis. There's also homeostasis between intracellular fluid and extracellular fluid. And guess what it is that regulates that? Tonicity of the water. So tonicity is influenced by the amount of particles, the amount of solute that is in that solution. Okay? A eosmotic cell, check this out. So a eosmotic cell that has just the right amount of sodium inside it and potassium inside it and all the electrons inside of it, that is surrounded by pure water with no electrolytes whatsoever. In that system, there is a 5,400 millimeter of mercury pressure differential across that cell membrane. 5,400 millimeters of mercury. Those are the same units we use to measure blood pressure. It's a huge pressure. So if you were thinking that the concentration of ions doesn't have much of an effect on pressures and movement of fluid, you were dead wrong. It has a huge effect. In fact, it has a bigger effect than blood pressure does. Again, a eosmotic cell, that is a cell that has just the right amount of intracellular ions. If you put that cell into a bucket of pure water with no electrolytes in it, the pressure exerted on that cell membrane would be 5,400 millimeters of mercury, just because of the differential between the highly concentrated ions and the zero concentrated ions. It's enormous, enormous pressures. These are very powerful forces at work. So an isotonic solution is one where the concentration of ions is the same in the solution as it is inside the cell. And as a result, there's no movement of water back and forth. And remember, it's water that moves in response to these concentrations of ions. It's the water that moves, not the ions. So again, an isotonic solution, we have the same concentration of particles in the solution as we do inside the cell membrane. A hypotonic solution is where there are fewer of these ions in the solution than there are inside the cell. And so when we put a normal cell into a hypotonic solution, then the cell swells because the fluid is what's moving, right? The fluid moves inside the cell to try to dilute what the fluid thinks is this hypertonic amount inside the cell. So a hypotonic solution where there's fewer particles in the fluid will force fluid into the relatively higher concentrated solution that's inside the cell, and that causes cell swelling to occur, right? The opposite is also true when you have a hypertonic solution, salt water, for instance, a hypertonic saltwater solution like 3% saline. That is going to force the fluid from inside the cell, which it thinks is, relatively hypotonic in relation to the fluid. It's going to force that water out to try to dilute the fluid out here. I want you to understand that there are several forces at work, and you probably, if you're like me, had no clue what the difference between osmotic and oncotic pressure was, and it was just confusing, and oh, the blood pressure has something to do with it too? Well, it does. So the osmotic pressure is the pressure that we just talked about. That is the pressure that is defined by the number of particles in solution and the ionization of that fluid, all right? So these are non-proteins that are dissolved in the blood. In this case, when we calculate the serum osmolarity, we calculate it by this formula. 2 times the sodium. So this is a pretty important number, right? The sodium is hugely important. And then we add in the component of the BUN and the component of the glucose and the component of any alcohol and add that all up together and we get the serum osmolarity. The serum osmolarity is the force acting to push fluids in or out of cells. Okay? It's the force that acts to move fluid in or out of cells. Now, when we talk about the capillary, we're talking about 2 other forces. One force that pushes water out, that's the blood pressure or the hydrostatic pressure. And another force that holds the fluid inside the vessel, and that is the osmotic pressure. Now, just to confuse things, they also call it the colloid osmotic pressure, which is stupid, but anyway, the oncotic pressure. Think of proteins, all right? This is the concentration of protein in a solution, and that is the force that acts to keep the fluid inside the vessel. Okay? So in this case, we're going to think about serum albumin. And clinically speaking, you've all seen patients with super low albumins. They come in, they have that mushy edema that just, it pits as soon as you touch it. And it stays pitted for an extended period of time. That's that mushy hypoalbuminemic. Yeah, that's right. Hypoalbuminemic mushy edema. So how do we calculate the oncotic pressure? I don't know. It's magic. Somebody does it. But let's just think about the serum albumin. And when we calculate when we talk about the oncotic pressure, we're just going to look at the serum albumin, and that will help us figure out if they are at normal oncotic pressure or low. All right. All right. So those are the three forces at work. This osmotic pressure works on moving fluids in or out of the cells. The hydrostatic pressure pushes fluid out of the capillaries. And the oncotic pressure is the opposite of it opposes hydrostatic pressure and tries to hold the liquids in the vascular space.